Καλησπέρα σε όλους.
Good afternoon, everyone. I would like to thank the chair, Mr. Tsirakis, and I'd also like to warmly thank Jean-Louis Scartazzini, for he really emphasized on the sort of cooperation there should be between architects and engineers. And this is very important. This is actually what I tried to insist on this morning on my opening speech. What we emphatically call bioclimatic design today is nothing more and nothing less than the rational approach of planning for technical projects. So this brings together the civil engineer, the engineer, mechanical engineer, and the architect. They're all working together, which means that in bioclimatic design, there is a set of parameters that we need to take into account, including the environment, topography, climate, the landscape, the city or town, respect for the environment, and energy management. No matter which way you might look around the globe, traditional architecture and projects are in line with rules and the technology that aligns itself with the nature, landscape, local climatic conditions, topography, the fabric of the city, and of course use of local material matters. What we are discussing about today, free cooling, has been there by tradition. So free cooling is not actually something that wasn't there. It's not every day that we discover the principles behind architecture and physics. Let me use this photo to remind you exactly what Professor Martin Rapp used to talk about. He actually talked about built land. Here you have an image, a photo of of houses in Galaxidi. They are not actually built with stone or bricks. They are made with earth and clay. They ought to remind you of something. I could, in a rather trivial manner, say that tradition is intertwined with our background and experience. So tradition is there to teach us. Every form and shape corresponds to particular circumstances. The fundamental materials for architecture are light, solar light, and the space. Solar light will give us the form, the shape. It's actually the one that will indicate the geometry. It's there for us to follow the geometry of the sun. Here you have Pittsburgh, Louis Kahn, Le Corbusier in Ronchamp. All the concerns about bioclimatic architecture are quite apparent, along with the basic fundamental principles thereof. They are obvious in major architects' projects and works such as Pikionis, who used local material, Konstantinidis, who played with the light and the shadow. He would just make terraces or gardens for daylight or maybe evening. And then Zenetos, who quite early had come to realize the importance of the sun's geometry, mostly through the Dimitri school he built, because he introduced a design that aligns itself with the course of the sun through the day. And so classrooms are quite protected in terms of intense solar light, but the overall, you see, outcome is quite impressive. So, before the majority of people realized there was an issue with regard to energy consumption and savings, before people actually thought about environmental protection, it seems that everything was there. It reminds us of the bourgeois gentilhomme of Molière, who had been speaking prose all his life without really knowing it. So the overall problem that contemporary societies are faced with is quite complex, because it regards the protection of our planet, the legacy and heritage of the planet which we need to preserve, quality of life that we need to preserve, our economies, production, peaceful balance for the sake of everyone on this earth, and the preservation and protection of our children's future. So this is all integrated in the notion of sustainable development and viable development. When we talk about planning, designing, and constructing buildings, there are some fundamentals that we need to bear in mind always. Like I said before, we have to bear in mind the topography, climate, urban characteristics, the environment. We have to carefully select materials we're going to use. We have to ensure there's solar protection, there's cooling, ventilation, renewable energy sources maybe will be used. Technical standards need to be preserved with a view to ensuring there's low energy consumption by those buildings. Let's not forget about the importance of actually raising the awareness of people and tenants properly using those buildings. And also, we need to be careful when it comes to our share of responsibility when the building will, quote unquote, eventually die. You see, engineers and people, the occupants, bear a fair part of that responsibility. Which brings me to the next issue at hand. No matter what the project we are going to work on may be it a bridge or a whole building, it all needs to follow a certain concept. I'll show you examples based on my experience and the ways I dealt with certain issues. This is not a recipe, it all depends on your individual methodology. It's just the way of thinking I'm going to show you. But these projects mostly regard projects that were constructed in Switzerland, where I've spent most of my career, and it's true that in Greece you might be dealing with these matters in a different manner. Nonetheless, the concept ought to be more or less identical. This is a simple house. It looks into the south. You have passive solar light, and here you have the north. You try to cut off the north, if you will. The main principle behind bioclimatic design is this. You have to have a fully insulated building, fully protected from the northern winds. And then you have to properly manage the building and position it properly, depending on the sort of outcome you have in mind. Here you have another example. It's been constructed for a number of years, but this was an experiment to me, a major experiment to me. Here you can see solar houses in Lausanne. This is just one out of many solar houses. And in this particular case, again, you have a house which is open towards the south, and it's quite protected and insulated, facing the north. This is a very oblong and narrow plot of land, but I hope I was smart in the ways in which I tried to bring together all of the options that passive solar light can help us take advantage of. Drum walls, I guess, are something you're familiar with. Maybe we're no longer using them. They were quite popular a few years ago. They were part and parcel of our experiments. We also have solar panels to get warm water, and we're also using those panels for heating. We also have verandas and greenhouses overall. We get the air through them, and we use that part of the air to complement on heating for the house. And then you have aeration systems, ventilation systems in the walls, and here I come to the issue of morphology because I touched on it before. Earlier on, we talked about bioclimatic design, and in this particular case, you have a narrow house, and you have the cross-section. We are aligning ourselves with the sun. We are using solar collectors, direct lighting, direct gains there. Greenhouse and drum walls are used. This house was designed in such a manner as to ensure there is natural ventilation and cooling in the summer. Moreover, this is a well-insulated house. We insulate it quite strictly, and we avoided thermal bridges. And of course, we are capitalizing on the light, the sunlight, depending on the geometry we opt for, of course. Natural light. This is a narrow house, remember? So we get the house to be lighted as best as possible. And we use certain tricks to make sure that light penetrates the house as best as we can. At the heart of the house, in the central part of it, you can still get great light in without having openings or windows. This is the lighting where you have no windows but nonetheless able light. Throne walls, moreover, as you know, they are charged, heated by the sun in winter. And so there you have thermal circulation, which helps keep the room warm. In this case, this whole system and methodology worked perfectly. And then you have the summer. And in this case, you have protection and at the same time contemporaneous, simultaneous cooling, ventilation. I am just touching on several experiments which we've been conducting since 1985 and through today. Here you have another photo, solar residential complex, close to Lausanne. In this case, the houses are positioned in such a way so as to avoid having one shadow the other. We are using several typologies. We opt for typologies to make sure we protect the houses from the cold, but we're also using methodologies to protect these houses from the noise. This is actually something that both Mr. France and Mr. Berriela touched on earlier on, because they both were concerned with protection against noises and noise pollution. In those very typologies, let's opt for one. In this case, you have the light penetrating the houses, just like I showed you before. So light goes into the house through slits we've opened, and so you have those openings that work on two levels, thus keeping the interior warm and having the light reflect to adjacent rooms. Moreover, here you have an aeration system of ventilation. You get warmth through the solar light that is coming in through the porches or the greenhouses, and you get, again, a dual system because the walls get warmed in the greenhouse, in the veranda or the terrace, and then there's a system which carries inside the house the air. This residential complex. Remember, we showed you earlier on blocks of flats that were two-story ones, but in this case, we are dealing with flats that take up floors, each one floor. So in this case, we use whatever generates energy. It's placed at the center, and the systems are linked to the verandas, be they in the north or the south. So the orientation will also help us also collect light. There you have an idea. And here you have the great thermal outcomes and results you can get energy-wise. We proceeded with an analysis of data collected from this particular complex. We used the Réseau lab, and we made a comparison between the data we collected and more traditional and less bioclimatic residences to actually assess the importance of consumption. I'm not going to dwell on that, neither am I going to elaborate, but this is to show you how much natural gas we use or solar power to heat water. And the Réseau, or the lab, also proceeded with an important analysis because, just like Mr. Cartesini said before, depending on the user, depending on the family, you may notice that some apartments have a minimum energy consumption and others exceed the average. And quite often you come across households which go beyond the confines you've said. Which brings me back back to what I said before, the role of the occupant, the role of the people who are going to take up a building, the individual consciousness is quite important, which brings me back again to Plazo, which, well, let me add one more thing as concerns the planning rationale. Because you see, in this particular case, we also drew on a traditional piece of thought. We used local wood. Wood is there, it wasn't painted, nor was it glazed, but we have shades and louvers there. You have a sort of roof on every story, on every floor. And I'm not going to give you the details because this has everything to do with what the previous speaker said before, which all goes to show that we are using this part of the building. So you get sunlight from the east, and these extensions mean that you have broken down to 3 layers every floor. You have the upper part, that's the lighting, and the lower part, which is the very strong insulation. So, in this case, we are capitalizing on those extensions, if you will, to protect the material, which is the wood. And I think that the building is in a rather good condition, even after so many years of having been built. So it doesn't call for more maintenance. Protection. So we have stratified protection in terms of protection from the sun, that is, and then you have the anadolic. Well, in this case, Mr. Cartesini again was quite elaborate, and he's explained everything. These are the extensions we were referring to. When we talk about bioclimatic design, we use wood in this case, wood being a material that has a negative consumption of CO2. Mr. referred to that as well, but we also have to make sure that we protect this natural material. You can't just use it as a decorative means. Each and every local material has its own features, its own specificities and character, if you will. So any constructor, any architect whatsoever, anyone who plans on using wood or any other material which is natural for that matter needs to carefully think about what they're going to do with it. One more complimentary note, if I may. We also analyzed the ecological cost of the facade. Les Eaux actually proceeded with that analysis a few years ago, and people there tried to calculate carbon dioxide emissions cost, and so that's the imprint, if you will. And here you have the analysis of materials used, and this slide shows you, moreover, the non-renewable energy, global warming potential, and acidification potential. And there you have, depending on the type of material, their respective consumptions. There's reference to metal, for example, and reference to other not so eco-friendly materials. And there's also reference to distance, way of construction, exploitation, use, if you will, by the users. In this particular case, Mr. Cartesini and his group, his team. And then there's reference to the distance from the work site. We had a group of workers, or rather we made a comparison. Red stands for the teams that worked on site because we hired locally, and then the grey color stands for potentially us hiring people and crews from another city. Another example that I will rush through again regards a free cooling system used in a school in Geneva. Again, we had a well-insulated building, and without opening the lights, you have a recyclage of air. We have the so-called Canadian well, because you see, in this particular case, you have the cooling of air that is being recycled recycled as it goes underground. What is important about this building is actually land use and economy. Whenever you build anything, depending on the form and shape that your building is going to acquire, you nonetheless leave an imprint on the land, on the plot of land. In this particular case, we were faced with a huge park. So on purpose, we decided that this would be a compact, the most compact building possible, just to make sure we save the park, have as much greenery, as many green areas as possible for the sake of the students. So we have the yard and the park all in one. The cross section will probably make you think of the previous house I showed you, one that I earlier showed you, where you have the light going in at all times. Here you have aeration, ventilation, cooling underground in the basement, and that's the result. One compact building, the envelope of which, the shell of which is clear. You have terraces that are green and great insulation, quite powerful. The result is very, very good. We were happy with the outcome. In terms of energy consumption, I think we are at 39 kilowatts per square meter on an annual basis, which is Minergie. How can you manage all problems that may emerge in case where you're working in an urban environment? In the cities, the conditions are quite difficult when it comes to sunlight and distances. Strong insulation is always important. But the closer we get to the object at hand, you have to look for light, you have to introduce protection at night time, and then you have to see what sort of light you're going to use, northern or the southern. And in this particular case, moreover, we've used strong insulation, a material which has a very low eco cost. Of course, this is not clay. It's not what Martin Rauch talked about, but then again, it's still quite an eco-friendly material, although it may be heated, and at the same time, we're using a system using thermal pumps, heat pumps. So we're using, legally, water from the aquifer. Certain surveys that were conducted by friends, amongst others, François Isler is a friend, but many architects have conducted such surveys. Let me open a parenthesis. Martin Rauch showed us how to use clay and brown, and in this case, Isler tried to conduct his own experiment. So he used recycled aluminum. It's a very interesting piece of thought. He just used aluminum profile, recycled. He thus created double glazed panes. Among the two panes, he uses ecological materials. It's just part of his research. Maybe he will use a straw or anything for that matter. In any case, thus he makes something that costs really, the cost of which is really, really low. And a few years ago, he also went on to try to not use foundations, which brings me to a very critical issue, because this now brings me to the Greek condition. What is the reality Greece is faced with in terms of bioclimatic designs? Because there are always wiser and smarter ways in terms of designing bioclimatic buildings. But like what we said this morning, in each and every country you have 50% of energy consumption which is due to buildings. Let me take the example of any Greek city. In the case of one Greek city, how can you try to cut down on energy consumptions because of this, of what you see on this photo? So energies are economies of scale, energy saving, bioclimatic design for existing and new buildings ought to take into account the fact that each and every Greek family apparently owns the apartment they live in. So you have blocks of flats, and now blocks of flats for Greece are actually a unit which is there, and there is lots and lots of blocks of flats that make the cities in Greece. This is a reality of the Greek urban environment, and this reality of ours is well entrenched into the idea of private urbanization, private residences, private uses for public areas, private uses for the landscape as a result thereof. And this concerns all the existing buildings in this country. So given all that, how can you manage to promote effective and efficient solutions that will work energy-wise in terms of managing old buildings, existing buildings? In order to indeed promote such energy-effective solutions, you will bump against several impediments. I've seen that and witnessed it firsthand. I'm not talking about red tape or bureaucracy, no. There are other impediments. For example, at the level of every block of flat, there seem to be problems among the tenants, problems among the owners, problems between the neighbors. So it seems that for every block of flats that wishes to save energy, there has to be 100% consent amongst all. This is tough. You can't insulate the blocks of flats from the outside because you have the verandas and balconies. You can't actually insulate individual walls, or you will bump into the property of the neighbor next door. Maybe the neighbor will object to us adding 6 or 10 centimeters of insulation to their wall, or maybe bridging somehow the gap. You have to change the windows, you have to change the frames. It's tough to get everyone to agree on that. So you have to remember that when you need to put a strategy in place, and these measures are nonetheless important. Let me also underscore the fact that an infinite number of air conditioning units has been put in all sorts of buildings. There's no control over them whatsoever, and I'm under the impression today, and I've seen the statistical data, it turns out that air conditioning, or rather energy consumption due to air conditioning, exceeds energy consumption for heating purposes. This, of course, is also linked to the fact that there's been a change in the habits of people because they all want to feel comfortable. And I guess we have to make all users agree and to convince them that it's important to have a joint approach in terms of managing energy consumption and energy waste. A one-day event like this one today will not suffice. We have to somehow bomb the general public with information and data to raise the awareness. Moreover, when it comes to energy-saving projects, it seems that the cost is quite high. But nonetheless, I'm under the impression that right now, even in Greece, we are not just working on saving energy on the basis of individual households, but there are also other solutions available on the market, just as long as there is a real economy working. Well, in a nutshell, this is what I've been meaning to say about bioclimatic design, and I've been meaning to point the great problems that existing buildings may generate, because we can solve the current problems and we can raise the awareness of people, but we have to make sure we improve the energy efficiency of existing buildings first and foremost. Thank you very much. Any questions? Please make sure a microphone is being used. Mr. Scartesini showed us a building you actually built. So this was your building, and I think that you also showed us a slide, and there is a fraction of the light, right? Because there is an anidolic shelf. And at the same time, there is also the lower window, which gets light in at the same time. So when you are dealing with an office space, an office building or a school, I guess this is not necessarily useful, and maybe it can actually be the cause of glaring, and it could be a problem, right? Especially in winter. In winter when the angles are low, small. Right, so this brings me back to this photo. When this building was built back in 1982, It consisted of 9 cells. Each and every one of the cells was equipped with an electronic facility that was linked to our computer. So you could intervene in individual cells and use buttons to change the values. So this was sort of automatic. You could actually use it from a distance, and this particular lab is oriented towards the south. And there is another thing. There is moreover a system, an independent system. In this case, when you get lots of light, this system protects the anadolic system. And the user themselves can protect and shade their own working area. This is a dual system to help people who are working at their desks keep in touch with what's outside. So you are sitting at your desk and working, but you can actually use that. You know that in winter you have light getting in, it can be an issue, but then again you, the user, can protect yourself. You have a sort of fabric there which you can lower as a louver, and you can get it there. Here's your working area, here is your anadolic element. I don't think that our dear friends have been getting lots and lots of light, have they? More questions, maybe? I've been meaning to ask you about the height of each floor. In those cells that you talked about, it's 3.2 meters. Net, yes. Thank you. You say that drum walls are no longer being used now. Was it on the basis of experience which showed they're not efficient or effective? No. You see, we've been working since 1978 in this particular field, and drum walls had begun before that. They were popular. Of course, Mr. Trom ushered them in, launched them in France, so they were in use before 78. Several investigations were conducted. I mean, Lezo conducted its own measurements. The physicians of the building were measuring data. All of that was actually the result of a cooperation. You see, it's not just I felt like using a drum wall today or not. So there were measurements, the results were rather positive, and they were used. But at that point in time, we were not faced with the same issues we are faced with today. Today we are going higher. We have higher, better, if you will, better models for energy saving. We aspire to get to zero energy levels today. Back then we were using other techniques, and we were assessing the hyper cost of constructions that was due to panels, solar collectors or drum walls. So we would calculate that back then and try to find ways through which we can actually amortize the cost through bringing down energy consumption. Back then oil costed less, significantly less. The price of oil was so lower, so back then we were looking for other measures and other ways, which were more sophisticated, if you will. We were trying to find more economical ways. Drum walls bring together a wall per se, a well-insulated glass pane, and then you have aeration, ventilation, protection systems, and so on. That's why I said that back then other parameters were at play. Now I would actually use drum walls. I've actually lived in this particular building. It works. The outcome is great. Drum walls are something that I would use today because drum walls help in the case of cells, in the case of rooms, and windows are comfortable, and you don't get lots of heat in the summer. My question regards heat pumps. Do you use the water directly or do you use an alternator? Of course, it's the latter. We send the water back to the other end of the building, and we are being controlled by the relevant authority, which shows up twice a year. They pay a visit to make measurements to find out whether whether the difference in temperature exceeds 4 degrees or not. So you see, we are being checked. And what about these pumps? Are they central or not? I can't talk about it right now here, but I can look it up and then I can get back to you, because we talked about so many things. I can find out for you. I think there is a COP which is about 3.8 or even 4. It's bordering of 4. Trombe walls were used without insulation, of course. Of course, it goes without saying. But you see, right in front, you have the double glass pane, so it's insulated. And there is the frame, which is also insulated. In this case, you have an aluminum frame that keeps heating outside. And I'll be very straightforward with you. In some of those houses, the shell is iron. It's made of iron because back then aluminum was a high consumption material. Today there is recycled aluminum on offer. And this is something that maybe Ms. Tracht would like to comment on. Because I think we can use, in a simple way, or in several simple ways, aluminum that's been recycled. So there's no bauxite involved. It's not very high consuming when it comes to energy consumption. So we can use recycled aluminum, right? And this is the main rationale behind the new uses. That's why Mr. Rao talked about research which is being conducted involving grass or soil or clay. I mean, today we shouldn't be building something up in the north of Evros, and you can't hire people from Crete. Costs are higher. We'll give you a rather silly example. Suppose you buy a box of orangeade, that's been flown in from Brazil, for example. This is 1 liter orangeade that equals 1,000 liters of water if you fly it in from that greater distance. I'm trying to give you the impression, the idea behind the whole issue of consumption. Unfortunately, a comment was made off mic. One addition, if I may. Because today we are faced with a chaos in Athens. You've showed us one photo. I never used the word chaos nonetheless. No, it's my personal description. So it's pretty chaotic right now in Athens. And right now in Athens there's a trend involving the use of air exchangers, air alternators in the boilers. So this helps save about 25% of oil that could be used, because in this case you have 200 degrees of emissions due to oil, and now you use those emissions and you also take advantage of the water that's being brought to the boiler. You thus heat the water, and there is some sort of small improvement that will not impact on our neighbors, and that wouldn't call for their consensus. Yes, thank you very much, says Mr. Papadaniel.